So I'm honored here to be here today to present my PhD thesis work. And this was carried out at Carnegie Mellon University. And it wouldn't have come together, obviously, without my, my great advisors, Chris Harrison and Scott Hudson, and my committee members, Benko and Jody Filizzi, and of course, all the collaborators I had from Carnegie Mellon University, Microsoft Research, and other institutions. So my thesis is titled On-World Interaction, or On-World Computing, rather, focused on enabling computational interaction with everyday surfaces, such as walls, tables, furniture, and so on. So ubiquitous computing seems to be here now. Like, we seem to actually have ubiquitous computing in the form of these smartphones. Billions of people own smartphones, and these are very, very sophisticated computers jammed into very tiny packages that we carry around with us constantly. So of course that means that smartphones have made computing disappear into our lives, right? Now, it's not quite true. If you actually want to interact with the digital world, you have to do it through that handheld terminal. And digital content is fully separated from the physical world. This isn't really the vision of ubiquitous computing. It's trapping the digital world in these little boxes. And so for my thesis, I set out to try to fix this, to bring computing out of the small trapped interfaces of today and out onto the world around us, out onto our everyday surfaces, our walls, tables, and furniture, and so forth. This is what I call on-world computing. This is bringing interaction out onto natural everyday surfaces and embedding computational capabilities into the real world. So now, one way we could do that is we could just transform our environment into computers. This is the easiest way, right? So we could replace tables with touchscreens, we could replace walls with giant TVs, countertops with tablets, and so on, until everything is interactive. The obvious downside here is the cost. You know, although computers might be cheap now, they won't be as cheap as drywall or wood anytime soon. And it's difficult to upgrade. Imagine telling someone, well, you have to buy Wall 2.0 next year. It's the must-have upgrade. And it still limits you to surfaces that are actually suitably augmented. But we already have a technology that can actually enhance environments at a distance, and that's the humble light bulb. So what I'm going to talk about today is showing you my research in taking this basic 1-pixel light bulb and turning it into an interface projector, something that can actually put touch interfaces on any surface in the environment. So I started my journey with a system called WorldKit. And this is an early project that I did to try to explore the potential applications and also the pain points that we might run into when trying to build on-world interactive systems. So WorldKit's a complete system, and what it lets you do is it's kind of a software toolkit for the world. Here, what I'm doing is I've written an application, and now I'm deploying it onto my environment. This is a status message app for my office. So when the door is closed, there's a touch sensor on the door. When the door is closed, I can let people know why my door is closed. So the application programmer here has basically defined sort of the behavior and the controls that the application needs, and then the user customizes the application for their environment by specifying where each of those controls go. And so how this actually works is, you know, there's a projector and a depth sensor that are fastened together and calibrated into a single unit that you point at the surface. This isn't the light bulb, you'll notice. And the depth camera here captures depth images 30 times a second. This is what one of those depth images looks like of a typical sort of office environment. And unlike an RGB camera, like a regular camera that you'd use, this captures distance to the nearest object, which is represented here as a gradient between light and dark. And at startup time, what we do is the WorldKit system will capture a couple of seconds of background and use that as a background model. So you can see here, this is a video of how that tracking actually looks in real time, how we actually track user input using the depth data. So we can detect differences in the pixel depth from that background model. So here, the regular green color is pixels that are at background, dark green is too far in the foreground, and blue is those pixels that are sort of close to the background, but still discernible as being different from it. So that lets you know where the user is actually interacting with the system. So this is how we do touch detection in WorldKit. And the second component is to do output. So in order for the WorldKit system to handle any surface at any angle, we have to do some sort of planar rectification. So the system detects essentially what orientation the surfaces are at using the depth camera, and then rectifies the image so that it appears correct. So on the left, you can see what gets projected out of the projector, and on the right, what you actually see when you're interacting with the system. And the other thing that's interesting about this is it makes it possible for developers to treat the whole interface as a collection of 2D planes. And this makes the development process, the actual programming process, very, very simple. But the big difference is that instead of pixels, developers have to think in real-world units, millimeters. So we deployed a couple of applications with this. So this first application is a sort of a recipe helper. What this does is each of these slots has a different kind of touch sensors here, and allowing the user to visually see when the recipe they've sort of assembled has actually been fulfilled. And this was actually deployed to Alzheimer's patients on a real kitchen table, showing that this improved their ability to complete sequential recipe tasks. And the second sort of little demo application here is my office application. So this is an augmented office with a very much younger me. You can see that the contact tracking here is pretty rough. I have to use my whole hand, right? So this is one of the things that's sort of a downside of the system. But I've got a little sensor on my keyboard here so that when I put my hands down, my private calendar pops up. So this is kind of a nice little way to augment my environment, and it's pretty unobtrusive. But on the other hand, there are a lot of challenges with this system. So first of all, the contact tracking, I have to use my whole hand for that, and that's not what we're used to when we're using touch interfaces of today. And the user interaction was very, very simple. It's just painting and hand tracking, not a lot more that I can do with that. It's up to the interface author to define any other interactions that might be possible. And the system doesn't really respond to its environment in any meaningful way either. I mean, it's an on-world system, but it's not really interacting with the world. And finally, obviously, that big projector is pretty unwieldy. So it'd be nice to try to shrink that down into something that's really more like a light bulb, or consider an alternative to projection. So in the rest of my thesis work, I set out to improve each of those areas. And so I'll start with input sensing. So this is a system called Direct. This is called depth infrared enhanced contact tracking. So what this actually does is it enables high precision tracking of the fingertips using only an off-the-shelf depth camera. And so you can see here, the filled green circles are direct tracking the user's fingertips, and all the previous methods in the literature that we compared against as these hollow circles. So why does direct perform much better than previous methods? Well, previous methods have really only used depth data alone. And if you only use depth data, you run into some really nasty corner cases. So on the left side, you can see this is what happens when I put my palm flat against the surface. You can see the fingertips are barely visible, and they're just sort of fading into the background. And on the right side, this is what happens if I put my finger at a very steep angle. You can see the actual fingertip is not visible at all. But a lot of these depth cameras capture infrared data as part of their normal operation. So if we get at that infrared data, we can see something very different. Obviously now the fingers are very, very visible. But if you only use infrared, of course, you can't track how close things are to the surface. So the key to direct is merging both of those. So in depth, it's easy to segment the arm and the hand and detect the distance to the table. And then in infrared, we can segment the fingertip. And so what direct actually does is it locates the arms, the hands, and then the fingertips in the combined image. And this kind of hierarchical model ensures that we can reject anything that's not really remotely human-like that's sitting on a random office table. And so this is sort of a picture of what direct setup looks like. It's still a depth camera, and it's still a projector. But you can see that direct actually offers a significantly better accuracy, as you can see by the bottom right picture, without any smoothing applied. So this is significantly advancing the state of art in terms of touch interaction. And we ran a user evaluation to direct using crosshairs and shape tracing. And you can see here, direct as that filled green dot performs significantly better than the comparison methods we found from the literature. And in point of fact, actually, from our crosshair test, we found that direct was able to achieve, on the left there, achieve an average accuracy of 4.9 millimeters in terms of mean error. And that's actually getting competitive with real capacitive, physical electrical touchscreens. That's pretty good, considering we're using a camera that's 2 meters above the surface. And for shape tracing, in fact, it's even better. It's around 2.9 millimeters error. So this is achieved all without any temporal smoothing, without any subpixel position correction, all sort of techniques that are commonly used in real touchscreens. So this is enabling the raw tracking to be significantly more accurate than previous systems. So this is good. We've actually managed to achieve kind of touchscreen level touch accuracy with the system. So that's kind of our first goal achieved. And so the next goal is to look at interaction. So building on-world interfaces that live on complex desk services. And so if you actually look at if you look at the literature about desk services, the existing literature kind of implies that we've gotten rid of everything that lives on our desk. It's really clean, clear, no clutter. But our desks probably look a bit more like this. There's lots of stuff on the desk. Other digital interfaces that might have to be projected on those environments are going to have to contend with physical objects for space. So I built a system to try to figure out how digital interfaces can actually coexist with these, and to figure out what kind of interactions people would want to use on their desk environments. So to do this, the first step was to run an elicitation study to figure out what people's expectations were regarding digital interfaces living on physical desks. So for example, what I did is have people use paper application mockups. So bring some different kind of applications to users and say, okay, where would you put these on the interface? How would you expect them to behave? What kind of interactions do you want to perform with them? So here, for example, the users placed a map on the left side because they don't use it much, a calendar B on the middle that they can sort of use and see regularly, and C and D, which are a music player and a keyboard, or a number pad rather, on the laptop so that they can actually augment the keyboard. And this is kind of an interesting fact, right? We can use digital interfaces to try to augment physical objects. And you'll also notice a funny thing, which is that users have actually arranged it sort of radially. This indicates that real physical desks don't necessarily correspond to sort of nice rectilinear grids like you'd expect on a computer desktop, but rather they might be arranged according to a completely different coordinate system, like this polar coordinate system here. So in the end with the elicitation, we derived several different controls: multi-touch input, window manipulations, launching, closing, etc. But users also wanted these applications to actually respond to their environment, for example, so that they could attach, follow certain objects, or move away if objects were to obstruct them, physical objects were to obstruct them. So to actually implement all of this into a real system, I built a system called desktopography, named after the fact that it essentially scans the topographical map of a user's desk, identifying different objects in the scene. And besides the standard touch interactions, it supports snapping and following behaviors by basically tracking object edges in the depth map. And it supports evading collapsing by using an optimization method, sort of like what Anna was talking about, to deal with actual changes in the environment. So this is by defining different costs and penalties, by saying, don't put interfaces over top of physical objects that already exist. It'll continually try to update the layout of the environment to deal of the interfaces to deal with any changes in the environment. And so this is what it kind of looks like in practice. So notably, these are basically standard touch applications. They could be web apps, Android applications. This, much more standard than what we did with WorldKit, which had custom sort of applications designed for WorldKit. So what we can do, the user can launch an application by summoning it like this. So they've got like a calculator application, for example. This now can snap it onto the laptop, and you can see it sort of shows you the different edges that you can snap onto when you do this. And the user can also resize them with this little nub in the corner, just like the desktop application. This is a responsive app, so it changes its layout when the layout changes. And the interesting thing here is, all these behaviors are implemented just with web applications, right? So here's what we're doing with the optimization. And this is basically the interfaces have actually moved away, automatically detecting that they've been occluded and moving to a more suitable location in the environment. Okay, so that's a set of sort of interactions. And there's sort of more work in my thesis, but I'm going through the high-level points here. A set of interactions that allow the user interactions and both environmental responses that work on practical desk environments. So for the last bit, let's look at how we can actually do output. So this is split into two parts. First off, what I actually looked at was an alternative to project entirely. So this is augmented reality, or head-mounted augmented reality. So what happens if, instead of projecting things on the environment, we project it to the user's eyes directly? So if you actually look at kind of the HoloLens, it's a pretty cool device. You can do bloom gestures, like this kind of hand gesture thing. You can do voice input and head gaze. But one of the things that's really missing is the kind of tactile feedback and precise position input that you get with touchscreens. So what I did was to add touch input into the HoloLens and call that MR touch, or mixed reality touch. And so this is actually really nice. It actually allows you to co-opt any surface in your environment as a touch surface. So this is essentially how it works. This video is showing what the user sees. This is a digital overlay on top of the user's first-person camera view. It scans the field of view. It looks for basically interaction surfaces, flat planes that are sort of appropriate to put down interfaces. And then this is showing sort of a debug output. This is essentially showing you which planes have been detected. And then what the user can do is just drag out a rectangle to pull up an app launcher. And so this is an interface. This is an interface, a virtual interface that lives in the environment that the user can see, interact with. Standard touch applications all work. And it also supports things like in-air gestures as well. So in this example, I can build a little blueprint for a building and just pull it out, just like that. So this can actually let you mix touch input, which is positionally very, very precise and lets you do a lot of really interesting stuff with hand gestures that expand the input vocabulary. So this is sort of getting the best of both worlds here, gesture input and touch input. So how that actually technically works, it's not actually that simple in terms of the technology. We actually have to, in direct, we had the advantage that the camera and the table didn't move relative to each other. But now the head's constantly in motion. There's no stability anywhere. So what this is actually doing is every single frame, it's running a ransack algorithm to figure out where the touch interaction plane is, and then to use a direct-like algorithm to detect the fingertips. With optimizations, of course, so that it actually runs on the HoloLens. We actually ran a study on this as well, found it achieves a similar 5mm mean error. So we can do the same sort of tracking as direct, but now from a constantly moving platform and sensing environment. So this is all self-contained, works entirely on the HoloLens, and actually forms part of the basis for Microsoft's next version of the HoloLens. So this is something that is being deployed for real. Okay, that's great, but we forgot one thing. This augmented reality is great, but we haven't talked about the light bulb yet. So what about that? So one of the things I actually did was to try to miniaturize those components so that they actually fit, into a very, very small environment. This is miniaturizing the projection and sensing components, which was presented last year at CHI. And I partnered with a hardware OEM called ASU to build a super small projection module and depth sensor. So in the bottom right, this projector is small enough to fit inside a smartwatch. So, and around it, we built a quad-core Android-powered smartwatch that projects a touchscreen onto your arm. And you're probably asking how long this lasts. It's about an hour of continuous projection or about a day if you're intermittently using it throughout the day. So this is how it actually looks when you're using it. And so the user swipes to unlock. This is pretty typical, the old sort of system. And that swipe to unlock is not merely for security or for sort of like play. It's actually a calibration procedure. So when the user drags their finger towards the sensor, it's telling the system what angle the arm is at, because that can change as the user uses the device. And then, of course, we support sort of standard touch interactions with this. So using a little tiny depth sensor that we built to detect the distance of the user's finger away from the smartwatch body. And so this is fully self-contained. The projector, the touch sensing, computation, power supply, we can get all of that in a very, very small package. So the next step is to really collaborate with them, build a real info bulb, something that has enough brightness, enough computational power to support sophisticated on-world interactions. So that work is ongoing. But the good news is, we've covered all of the challenges I outlined at the start. So, there's always more to be done here, but certainly in my thesis, I think I've pushed the state of the art in terms of input, interaction, and output. And I hope I've convinced you today that on-world interaction is not only desirable and useful, but that it's also practically achievable in the near future. So, thanks for listening, and a quick plug right here. I just started my professorship at the University of British Columbia, so I'm actively looking for students, so if you're interested, drop me an email, and I'll take questions.
Thank you. So let's have one question before we ask all three.
Nobody has any questions?
Yeah, it's amazing work, Robert. I have maybe a naive question, but obviously the resolution of like projecting is a lot more than would it be on a screen. Are there particular applications that you think where the resolution doesn't really matter? Do you mean, or what are the kinds of things where it's not going to be very viable if the resolution is not higher? If that makes sense.
That's a really good question. So things like there's actually so the recipe application, I think, is a great one, where you can sort of see it at a distance, right? Where you have it sort of laid out on your environment. Certainly, for someone who's not an Alzheimer's patient, we would, you know, have something a bit more compact, but something that you can use at a bit of a distance, right? We're not thinking about things that you would use right up close. Certainly, the resolution does become a problem, so you can't do very, very small text. But I think things that, you know, if you sort of imagine the sci-fi vision of like having, you know, the weather shown on your wall when you wake up, kind of thing, or when you want to do some simple interactions with that kind of content, or for things like even, you know, having wallpaper that changes dynamically. So there's all sorts of applications, I think, in that sphere that would work. But I think I'm not advocating replacing the digital interactions, the devices that we use today, but simply having computation be more ambient. Yeah.